Alright, so today's lesson is 7.5. We're going to be looking at scalar and vector projections, which come from the dot product that we've been working on the past couple of lessons. So I've mentioned this in the dot product lesson, but you can imagine that we have some vector b here and some vector a here. Now you can almost think of it as having a flashlight here, right? And the flashlight shining down, and you look at the shadow that vector A makes on B, which would be a perpendicular shadow. And that we call the scalar projection. Now the vector projection would just be the same thing, except it has a direction in the same direction as B. So how are we going to calculate these? Well, I said it comes from the dot product, so let's start with the dot product. Here we have vector A, and here we have vector B. So our dot product, A dot B, our geometric dot product, is the magnitude of A times the magnitude of B times the cos of theta. But you see, I've rearranged it slightly. I've put the magnitude of A next to cos theta. Because if we think of this as just a right angle triangle, which it is, right? That's a right angle, you can calculate for this adjacent side knowing the hypotenuse and the angle. The adjacent side would be equal to the hypotenuse times the cos of the angle. So this portion right here is our scalar projection. So if we rearrange to solve for it, we get our scalar projection, or we say the projection of A on B, to be the dot product of A and B divided by the magnitude of B. Now you can see that it doesn't really matter about the length of B, whether or not B is short or B is long. The scalar projection of A on B is going to be the same thing. You're going to get the same shadow. However, we will see later in the first example that we're going to do what will happen if that angle is greater than 90 degrees. If it's equal to 90 degrees, well, you can see that the dot product would then be 0 because these two vectors are perpendicular. So our scalar projection would also be 0. Alright, so we have our scalar projection. What about the vector projection? Well, the vector projection is the same thing as the scalar projection, at least the magnitude is. But then we have to multiply that by a unit vector in the same direction as B. So we've talked about unit vectors before. What we do is simply take that vector B and divide it by its own magnitude in order to get a vector in that direction of magnitude 1. So on the denominator, we get the magnitude of B squared. On the numerator, we have our dot product, and that is multiplied by our vector B. All right, so let's try some examples. Example number 1, we're actually going to show that the scalar projection of A on B is identical to the scalar projection of A on 2B. So I'm drawing this out. If you had, let's say B here, and then 2B here, so B and then 2B, and then we had some vector A. Geometrically, we can see that the projection of A on B is not going to matter whether or not the length of B is this long or this long. But let's see how that works algebraically. So first, our projection, this is how we write it. We're going to write the projection of A on B, and since it's a scalar projection, we're going to say the magnitude of that, equals the dot product of A dot B over the magnitude of B. Alright, what about the projection of A on 2B? So we'll write A on 2B equals, again, we're going to have A dot 2B all divided by the magnitude of 2B. And you can see if we use the associative property for our dot product, which was from lesson 7.3, we can pull that 2 out and just write it as 2 times the dot product of A and B. And we can do the same thing with our magnitude. That is just twice the magnitude of B. So our 2's cancel, and we get the same thing as above. So the projection of A on B is the same as the projection of A on 2B. Now part B, this is part A. Part B says show algebraically that the scalar product of A on B is not the same as A on negative 2B. Alright, so here is the projection of A on B. I'll just go over to the side here, and let's do the projection of A on negative B. So what does this look like? So negative B is in this direction then, and A is still something like that. So A and negative 2B. Well, if we're going to take the projection, taking the projection over here, so what does that mean? What do we get? Well, we do the dot product of A and negative 2B, and we divide that by the magnitude. Oh, sorry, not 2B, just negative B. And we divide that by the magnitude of negative B. Now we can use the associative property again and pull out that negative. So that's the same as negative times the dot product of A and B. But the magnitude of negative B is the same as the magnitude of B. So that just gives us the magnitude of B. So now this isn't the same anymore. The projection of A on B is this, which is right here, except now we have that negative. So when theta is greater than 90 degrees, you can see you're going to get a negative projection. Okay, so let's move on to the second example. I'm going to have to do this on the side because I used up my space already. So it says for vectors A here and B right there, calculate each of the following scalar projections, A on B and B on A. So make a prediction. Do you think the projection of A on B will be the same as the projection of B on A? What would this look like if we drew something like that? Let's just make up some vectors. Let's say this is B, and let's say this is A. Well, the scalar projection of A on B would be down to there, and the scalar projection of B on A would be to there. So are those the same? Obviously the direction is not the same, so you might be able to predict that, no, the vector projection would definitely be different. But what about the scalar projection? Is it different? Alright, so let's start with the projection of A on B, the scalar projection. So projection of A on B is going to equal their dot product, so A dot B, divided by the magnitude of B. Alright, well let's work through those. So A dot B, so we have minus 3 times minus 2, it's going to give us 6. And then our y coordinates, so 4 times 2, so that's 8, so plus 8. And our z coordinates, 5 root 3 times negative 1, so minus 5 root 3. So there is our dot product. And the magnitude of B, well, that's the square root of minus 2 squared plus 2 squared plus minus 1 squared. So when we do that on the numerator, we get 14 minus 5 root 3. And on the denominator, we get the square root of 9, which is 3. And that is approximately equal to 1.78. Okay, well, let's see then what the projection of B on A would be. So the projection, the scalar projection of B on A is again our dot product, B dot A, over the magnitude of A. Now the dot product of B dot A is the same as A dot B. So we know that's going to be 14 minus 5 root 3. We've talked about that before. And the magnitude of A would be the square root. We just go back and look at A. So it'll be minus 3 squared plus 4 squared plus 5 root 3 squared. And that gives us, if we add them all, the square root of 100, which is just 10. And all of that is approximately equal to 0.53. So no, the scalar projections of A and B are not the same as the scalar projections of B on A. Now our last question asks to find the vector projection. So this is a two-dimensional problem, so that's easy to draw what this looks like. Do it right here. So first vector is OA, so starting at the origin, and then 1, 2, 3, somewhere here and up here, so 4 and 3. So there is our first vector, where that's point A. We can just call that vector A. And then this is at 4 and negative 1, so about there. You can call that vector B. And so we're trying to find the vector projection of A on B, which would be somewhere here, but then it would also be in the same direction as B. So doing that, we have the projection. I'm not going to write magnitude signs this time, of A on B. That is going to equal our dot product, so A dot B, and is going to be over the magnitude of B squared multiplied by our vector B. Alright, well, let's start with the dot product of A and B. So we have 4 times 4, which is 16. 3 times negative 1, so that's negative 3. And then the magnitude of B squared, that's just 4 squared plus negative 1 squared. So 4 squared is 16. Negative 1 squared is 1. Multiplied by our vector B, which is 4 and negative 1. So this gives us 13 over 17 times 4 and 1. Now we could leave it like that if we wanted to. Our vector has a scalar multiple of that. Or we can write it as 52 over 17 as our x-coordinate, and our y-coordinate would be minus 13 over 17. So there's our vector projection of A on